Welcome you all to Principles of Organic Synthesis. At present, we study about base catalyzed carbon-carbon bond formation. So far, we have seen two lectures in this topic. The first lecture we studied about the aldol reaction, the reaction of aldehydes and ketones in the presence of base to give aldols. The second lecture we have studied Perkin reaction, the reaction of aromatic aldehydes with acid anhydrides, the presence of base. Then we studied Claisen condensation, where the reactions of esters with the base was demonstrated. Then we studied about the reaction of alkyl nitriles using base, which was called Thorpe reaction. In the lecture, we study about the reaction of enolates with alkyl halides and alpha beta unsaturated carbonyl compounds. This slide shows about the pKa value of the acidic protons. When you look this CH bond of the acetylacetone, pKa value of this protons is 8.84. When you replace one of the methyl group with ethoxy group, the pKa values of this proton is increased to 10.7. This is because this electrophilicity of this carbonyl group is now reduced comparing to that due to the ethoxy group, which can donate electrons more. It can reduce the electrophilicity of this carbonyl group. Therefore, the acidity of this proton is reduced. And when you replace this methyl group with another ethoxy group, the pKa value of this proton is further increased. The acidity of this proton is further decreased because both sides have the less electrophilic carbonyl group comparing to this acetylacetone carbonyl group. Here the resonance stabilization of the enolate of acetylacetone shown here. When you deprotonate, you generate the carbon ion, which can be stabilized by the carbonyl group as the enolate, as you can see here. So, this is resonance stabilization of the enolate, and here some of the other active methylene compounds are shown here. Here this CH bond, this methylene group also is bonded with 2 electron withdrawing group, nitrile group. The pKa value of this proton is about 11.2, and you can also replace one of the nitrile with the ester group. Now, the pKa value is reduced, this because this is more electron withdrawing group compared to nitrile. Therefore, the acidity of this proton is increased. If you replace the nitrile further with the nitro group, this is more acidic because this is strong electron withdrawing group. The acidity of this proton is further increased. pKa value of this proton is 5.8. When you replace this ester group with the nitro group, the acidity of this proton is further increased. pKa value of this proton is 3.6. Now, let us see the reaction of some of the carbonyl compounds. Now, let us start with ethyl acetoacetate, this 1,3-diacarbonyl compound. When you react with sodium ethoxide, already we have seen the first and second lecture. If you have this ester, you have to use the corresponding sodium ethoxide. This is because in case if it undergoes 1:2 addition reaction, then you will get the starting material back. When you now treat this sodium ethoxide with the ethyl acetoacetate, it can deprotonate this acidic proton, you generate the enolate. So, this enolate can undergo SN2 reaction, substitution. You can introduce methyl group here, and once if methylation is done, you have another acidic proton. It can be deprotonated with another molecule of this base. So, after deprotonation, you will have this enolate. this further undergoes reaction here via SN2. So, you can get this dialkylated ethyl acetate. Sequentially, you can do first you can do reaction with methyl iodide, which can be further reacted with base to deprotonate this acidic proton. You can have the enolate, that enolate can further undergo SN2 reaction with this allyl chloride. You can have this derivative. So, this when you react with the base, you can do hydrolysis in the presence of sodium hydroxide. Hydrolysis of this ester group can give this carboxylic acid. This carboxylic acid, when you heat, it can undergo decarboxylation to give this keto derivative. So, this can be explained as have this one. So, in this way you can remove carbon dioxide, you will have the this can convert into this keto compound. So, now let us look at the reaction of ethyl acetate with 1,3-dibromopropane. As we have seen earlier, and there we have seen the reaction of two different alkyl halides. First the reaction of methyl iodide, then we have seen the reaction of allyl chloride. In this case, the substrate undergoes reaction as we have seen earlier with base to form the enolate. So, this can undergo reaction here via SN2, you get this alkylation compound, and once you form this one, now the base can deprotonate this proton, you form this carbon ion, which can exist in the form of enolate, as you can see here. Once we form the enolate, in this case what happens here, this undergoes reaction, SN2 reaction, and you get the cyclic ether. First C alkylation takes place, the next step O alkylation takes place to give this cyclic ether as the product. Now, let us look at this substrate. This is, you have both side ester group. When you do deprotonation using sodium ethoxide, you can so enolate, as we have seen, it can undergo reaction here by SN2 pathway, you generate this alkylated compound. Now, this can further undergo deprotonation with the base. You have bromide. Now, this can undergo reaction intramolecularly by SN2 pathway, and you have this product. So, you form here the cyclobutane derivative. Once you form this one, as we have seen earlier, you can do hydrolysis of this ester group. Base hydrolysis can generate the carboxylic acid, and when you heat carboxylic acid, it can undergo decarboxylation to give this cyclobutane carboxylic acid. So, if you look at in the first case, we have seen the reaction of two different alkyl halide, methyl iodide and allyl chloride, and then the second example, the substrate was same. We have seen the intramolecular alkylation, first intermolecular followed by intramolecular. In this way you can make this cyclic ether. Next we have seen both steps, this also intermolecular followed by intramolecular alkylation takes place both via SN2 pathway. However, in this case the formation of cyclobutane derivative takes place. Now, let us look at the reaction of lithium enolates. When you have a ketone, if you treat the ketone with LDA, which can be generated if you have diisopropylamine react with N-butyllithium in THF at 0 degree, you can form LDA is strong base. When you add the ketone to LDA, you can generate this enolate. And this reaction is to be carried out at a low temperature -78, usually in THF. As higher temperature, the lithium enolate is not stable. So, this enolate once we have, you can react with the electrophile. For example, if you add aldehyde, it can undergo 1 to addition here, you can get this lithium alkoxide. When you do work off, you can get this aldol product. This is well known in the literature, well explored. Now, instead of aldehyde, if you add alkyl halide, it can undergo substitution via SN2 pathway. So, you get the CC bond formation. So, this you have to remember one thing in this, you have to add your ketone to the LDA in THF at negative temperature, you can generate the enolate. Once you form the enolate, and then you can add alkyl halide, the alkylation takes place, you can get this compound. You can warm up to 0 degree and they can get this CC bond formation. This is one of the important transformation in organic synthesis. Here some examples are shown here, and this first reaction shows the reaction of the ester with this alkyl iodide to give this compound. The deprotonation of this can generate this enolate, and once you form here, this can undergo substitution via SN2 pathway, you can get this compound. The reason to use of this tertiary butox group is that you should have bulkier substituent, otherwise what may happen once you form the enolate, this enolate can also undergo reaction with another ester, you can get Claisen condensation product. To minimize the byproduct, they have used here bulkier tertiary butyl group. Therefore, the condensation of 2 esters can be avoided. Basically, you have to form this enolate. Once you form the enolate, which can undergo substitution via SN2 pathway, so you can get the alkylated compound. Here the base is lithium. They use the bulkier base to minimize the Claisen condensation product. The second lecture we have seen esters can undergo condensation, the present base to give the 1,3-dicarbonyl compound, that is called Claisen condensation. To avoid that, and they have used here bulkier substituent and bulkier base, so that the enolate can selectively undergo substitution to give this alkylated compound. The second reaction involves the alkylation of carboxylic acid. Here you have to use 2 equivalent of lithium. The reason is that this proton is acidic, deprotonation of this can form lithium salt. So, now once you form this one, the another lithium can deprotonate this acidic proton, then you will generate this lithium enolate. Once you form this one, then it can undergo SN2 reaction as we have seen earlier, you can get the alkyl compound. Now, let us look at this amino acid derivative here, N-Boc producted amino acid. Here you have the acidic proton here, you also have amide proton, and then you have this acidic proton. So, you have 3 acidic protons, therefore, they have used here 3 equivalent of LDA. You form this intermediate when you add 3 equivalent of LDA. Once you form this one, now this can undergo substitution, you can get this product. So, after the reaction, you have when you do the workup, aqueous workup, you get the carboxylic acid derivative. So, in this way you can make substituted phenylalanine derivatives, because it is easy to remove this carbamate group. You can using trifluoroacetic acid in dichloromethane at 0 degree, you can remove this carbamate group, you can get the amino acid derivative. So, this slide shows about the kinetic versus thermodynamic enolates of ketones. Now, let us look at this ketone. You have 2 kind of acidic protons. This is more acidic comparing to this, and also less sterically hindered, this proton. So, when you have LDA at -78 in THF, when you add this ketone, you can selectively deprotonate the less sterically hindered more acidic proton, you can generate this enolate selectively. So, you have to have a strong base like LDA, short reaction time, and low temperature. These are very important. So, you can form this enolate. Once you form the enolate, you can add methyl iodide or any alkyl iodide, it can undergo reaction selectively, you can get the corresponding alkylated product. For example, you can get this one. On the other hand, if you treat with base like potassium hydride at higher temperature 0 degree or room temperature, the deprotonation takes place here, it will exist in the equilibrium form, and once you form this enolate, this can react with another carbonyl group ketone, it can act as a base, it acts as acid, it can, what will happen, it can deprotonate this one, you can form this enolate. And in this way you form the starting material, you form this enolate. This is more stable. This is called thermodynamically controlled enolate, because this more substituted, more stable one, when you prolong the reaction, this kinetic enolate, whichever you form, it is converted into thermodynamic enolate, more stable one, which can be reacted now with alkyl halide. So, you can undergo SN2 reaction as we have seen here, you can in this case you get this compound. So, controlling the reaction conditions, you can try to selectively alkylate this carbon or this carbon using. So, the reaction condition shown here, if you want to deprotonate the more acidic proton, you have to use strong base at low temperature, shorter reaction time, you have to quench with electrophile, the substitution takes place. On the other hand, if you want to generate the more substituted stable enolate, then you have to carry out at higher temperature. You can use a base like potassium hydride, you can form this more stable enolate. This can further react with alkyl halide via SN2 pathway to give this substituted ketone. So, the condition shown here, and this can be carried out, and if you approach solvent, if you use THF with base like potassium hydride, you can form. Alternatively, you can also form this enolate using potassium tertiary butoxide in a tertiary butanol, it can act as a proton source. You can form this enolate, then further you can react with alkyl halide to give this alkylated compound. Let us see one example here. If you remember the beginning, we have seen the alkylation of the active methylene protons. Deprotonation of this methoxide or methoxide we have seen, then when you react with alkyl halide, you can get this alkylation in this carbon. On the other hand, if you want to alkylation selectively, so you have to do deprotonation of this, and if you compare this is more acidic comparing to that. Therefore, what you have to do in this case, first you have to react with sodium hydride, you can deprotonate this proton, you form this enolate. Once you form the enolate, this can exist in resonance form as shown here. Once you form this one, now when you add another equivalent of base, for example, N-beta lithium, it can now deprotonate this proton, you form this lithium enolate. Once you form this one, now when you react with alkyl halide, for example, in this case, now it can undergo via SN2 pathway, substitution you can get this, then when you do workup you will get back. So, if you want to do alkylation in this carbon, and so as is shown here, you have to first react with sodium hydride, you form this enolate. Once you form this one, when you add another equivalent of base N-beta lithium, then you can generate the lithium enolate, which can undergo substitution with this allyl bromide to give this ester derivative. So far, we have seen the reactions of 1,3 dicarbonyl compounds and ketones, amino acids and carboxylic acids. Now, let us look at the other related compounds. This reaction shows the alkylation of alkyl nitrile, benzyl nitrile, with propyl bromide in the presence of sodium hydroxide. They have carried out the reaction in the presence of ammonium salt. This ammonium salt here acts as a base transfer catalyst. This reaction is to be carried out in biphase system, organic phase and water. The reason is that because sodium hydroxide can react with this one, then you will make propanol. To avoid that, this reaction has been carried out in the biphase system using phase transfer catalyst. What may happen here, this organic phase, your substrate will be there. In aqueous phase, you have ammonium salt, which can react with sodium hydroxide. You form ammonium hydroxide plus sodium chloride. So, this can dissolve in partially in organic solvent. Now, it can deprotonate this proton, you form the enolate that can be stabilized by the nitrile group. You will form. So, this can exist as nitrile enolate anion. Once we have this one, now this can undergo reaction here, and what you do, you generate bromide plus product and water. This you generate in the medium, the water will go here, and similarly this also can exist equilibrium with this one, then again it will react, in this way it goes. So, it is a the reaction is to be carried out on biphase system to avoid the reaction equilibrium substitution of the sodium hydroxide group with this bromide. And then it, so what happens here, reaction of this can generate this ammonium hydroxide, which can be sparingly soluble in the organic solvent, which can act as a base. Deprotonation takes place, you form this nitrile enolate anion, which can undergo substitution, and where you generate this ammonium bromide. This ammonium bromide can now react again with sodium hydroxide. In this way you generate ammonium hydroxide goes. You need catalytic amount of this one, you need stoichiometric amount of sodium hydroxide in this reaction. Now, let us look at this example. This is intermolecular reaction. You generate the anion here, which undergoes SN2 substitution, and you get this compound. And in this intramolecular reaction, as you can also generate the anion by deprotonation of this proton. Once you form this one, it undergoes intramolecular SN2 reaction once again, you can get this cyclopropyl nitrile. There is also possibility of reaction with sodium hydroxide, can also undergo reaction, you can generate alcohol, but that is slower comparing to the intramolecular cyclization. Under these conditions, you get this as a major product. The other example is dialkylation of this nitrile. For example, so since this is more acidic, even you can deprotonate using weak base, neutral base like triethylamine, it can deprotonate and form this anion. Once you form this one, it can now react with the benzylic carbon. Since electrophilic nature, then you get the substitution product. You will have so now the base can deprotonate again this proton, acidic proton. You generate the anion, which can undergo reaction with another molecule of benzyl bromide, you can get the dialkylated compound. Now, let us look at the reaction of nitroalkanes. Here the reaction of nitromethane is shown with alkyl iodide, and when you react with the base like butylithium, you can deprotonate and you have this stabilized anion. So, once we generate this one, which can undergo reaction with this by SN2 pathway, then you can get this compound. Similarly, in this case you have this acidic proton, you can deprotonate, generate the anion which is stabilized by nitro group, which can undergo substitution reaction here via SN2 pathway, you can get this substituted nitroalkane. Now, let us look at this one. These two, if you look at, both are intermolecular reactions. This is an example for intramolecular reaction. When you react this nitroalkane with potassium carbonate, so deprotonation of this can generate so which can undergo intramolecularly the substitution to give this cyclic nitroalkane. And this slide shows about the reaction of alkynes. when you react this alkyne with the sodium liquid ammonia, you generate a sodamide that can deprotonate this acidic proton, you can generate this anion. So, this anion can undergo substitution here with this dihaloalkane. This is the more reactive halogen. So, the substitution takes place here via SN2 pathway to have this acetylene derivative. So, this alkyne derivative can undergo further nucleophilic substitution with this cyanide ion via SN2 pathway to give the corresponding nitrile derivative. Once if you have the nitrile derivative, it can be converted into carboxylic acid by hydrolysis. So, this can be partially reduced to oleic acid using Lindlar catalyst. So, here the crucial step is this one, formation of this anion. Once you form this anion, which can undergo substitution with this dihalo compound via SN2 pathway, you have this chloro derivative, which can undergo another substitution with the cyanide ion to give the nitrile derivatives, alkyl nitrile, which can be hydrolyzed to give the carboxylic acid. Then partial reduction of the carbon carbon triple bond using Lindlar catalyst can produce this oleic acid. The next example is the reaction of acetylene with formaldehyde in the presence of copper iodide ammonium chloride. You will generate this derivative, which can undergo addition reaction with formaldehyde. So, you can get this alcohol. The diol can be reduced to saturated diol, which can be converted into tetratetrafuran. This is a commercial process using phosphoric acid, and this also can be further converted into butadiene using sodium phosphate at elevated temperature. Similarly, the diol also can be oxidized to succinic acid. So, this diol, when you react with hydrogen bromide, you can make the bromo compound, can be further reacted with sodium cyanide by nucleophilic substitution. You can get this dinitrile alkane. Once you form this dinitrile alkane, it can be further reduced to this amine, diamine, and alternatively you can also do hydrolysis, you can get this adipic acid. So, condensation of adipic acid with this hexyl diamine can give this nylon 6,6. So, this is one of the important transformations for the commercial production of tetratetrafuran, butadiene, and also adipic acid and hexyl diamine, and which condensation of this gives this nylon 6,6. This also can be used to produce succinic acid. An example shown here, conjugate addition. So, this ketone you have, as we have seen earlier, you have two acidic proton. This is more acidic proton, this is less acidic, and depends upon the reaction conditions. As we have seen, if you carry out the reaction at low temperature using strong base like LDA, the deprotonation can take place here and you generate the kinetic enolate, then alkylation takes place. But in this case, what happens here, and the reaction has been carried out using sodium ethoxide at higher temperature, and the deprotonation takes place here and you generate this more stable thermodynamically controlled enolate. More stable enolate formation takes place because you use the base at higher temperature. Once you form this one, so this enolate can undergo addition, you will form this one. Once if when you do the workup, you can get this compound. Alternatively, this also can be, now there is a possibility that this can also, this is again this more substituted enolate, this can be converted into this enolate. Once you form this one, now it can undergo intramolecular. Suppose in this case 1, 2, 3, 4. When you do reaction here, so when you add here, you form 4-membered ring, is not peaceful. Therefore, so when you form this enolate, this can undergo intramolecular cyclization, you can get this compound. Once you form this one, dehydration of this can give this one. So, basically if you look at here and you can, the enolate undergoes addition with this methyl vinyl ketone, conjugate addition, you get this addition product. Then the second, the base also can deprotonate, you can generate this enolate which undergoes further reaction, condensation with this carbonyl group, you do aldol reaction, which can be converted into this alpha beta unsaturated carbonyl compound by dehydration. This slide has some more examples. Let us look at this one, diethyl malonate. Here the substrate is wrong, it should be this one. When you react with the sodium ethoxide, a deprotonation of this proton can generate the anion, which can undergo addition. With this you will get this compound. Once you form this one, the sodium ethoxide can deprotonate this acidic proton, which can undergo a reaction intramolecularly with ester. You can form this cyclic 1,3 ketone. Now, let us look at, and here the reaction of nitromethane is demonstrated with this alkyl halide. When you react with the cesium carbonate, you can generate this anion. You can generate the anion which can be stabilized by the nitro group. This can undergo reaction with this double bond to give the Michael addition product. Once you form this one, now the base can also deprotonate this proton, then you will have this anion which is stabilized by the nitro group. This can now undergo SN2 reaction to give this cyclic nitro compound. In both the cases, if you look at first, the addition reaction takes place, then in this case condensation takes place, the whatever enolate is generated from the ketone which undergoes reaction with the ester group, and you get this 1,3 dicarbonyl compound. In this case, the Michael addition gives this product. Once you form this one, the base deprotonate this acidic proton, generate the anion, which undergoes SN2 reaction with this carbon to produce this cyclic nitro compound. In summary, first we have seen the reaction of enolates with alkyl halides. We have mainly seen the reaction of 1,3 dicarbonyl compounds, and the alkylation can be carried out by deprotonation of the acidic proton followed by nucleophilic substitution. Then we have seen one example where the regioselective alkylation, if you have for example, methyl acetoacetate, if you want to do alkylation of the methyl carbon, then you have to first react with the sodium hydride followed by butyllithium. You can generate the lithium enolate, which can undergo selectively reaction with methyl iodide. In this way, you can try to react with the methyl CH bond to give the corresponding alkylated compound. Then we have seen the formation of enolate from ketone. You can try to generate kinetic versus thermodynamic controlled enolate by controlling the reaction conditions. If you carry out the reaction at low temperature with a strong base like LDA and shorter reaction time, you can try to generate kinetically controlled enolate, which can be reacted with alkyl halide by a substitution to give the alkyl derivative. Alternatively, you can also generate the more substituted thermodynamically stable enolate at a higher temperature, and which can also be selectively reacted with alkyl halide to give the corresponding alkylated compound. Following that, we have seen few examples for the reaction of alkyl nitriles and nitroalkanes. You can deprotonate the acidic protons. The anion whichever you generate can undergo reaction with alkyl halide via SN2 reaction to give the corresponding alkylated nitriles and nitroalkanes. We also have seen the reaction of alkyne with alkyl halide. You can deprotonate the acidic proton using base, which can be reacted with alkyl halide via nucleophilic substitution to give this substituted alkyne, which has been used to synthesis of oleic acid. The second example we have seen, you can also react, for example, acetylene with copper iodide, the presence of ammonium chloride. You can make the corresponding copper derivative, which can be further reacted with like formaldehyde via 1,2 addition. You can make this alcohol that can be further converted into tetrahydrofuran or adipic acid, hexyldiamine. Condensation of hexyldiamine with adipic acid can give the nylon 6,6. At the end, we also have seen the addition of enolate to alpha beta unsaturated carbonyl compound, and first we have seen the Rabin annulation, where you can generate the thermodynamically stable enolate, which can undergo addition reaction with this methyl vinyl ketone that can be further reacted with base to give the deprotonated enolate, which can undergo addition with the carbonyl group to make the bicyclic ketone. And also we have seen the addition of diethyl malonate, the presence of base with alpha beta unsaturated carbonyl compound to give addition product, which can be further reacted with base to give the cyclic derivative. We also have seen the reaction of nitroalkane with alpha beta unsaturated carbonyl compound can give the substituted nitroalkane, which can be again deprotonated using base that can lead to nucleophilic substitution to give the cyclic nitro compound. With this, we will conclude this lecture. Thank you very much.